we're going to have the vector equation of a line. So if we have a line passes between 2 points, line passes between 2 points. Let's say we've got point 1, point 2, and we've got vector A. I'm going to use A1, A2 is my vector. Points, I'm going to say this is x1, y1, and this is going to be the point x2, y2. So, we've got a vector. There's P1, there's P2. We can write a vector that begins at P1 and ends at P2, right? What would the vector P1, P2 be? Take a step back. Started with those 2 points. I said, here we go through them, P1 to P2. Find that as a vector. I'm taking away the numbers. It's going to be the difference of the x's. It's going to be x2 minus x1. I'm going to kind of go on a separate line because I ran out of room there. Y2 minus y1. So we can write from one point on that line to another point as on a line as a vector. If it's parallel, 2 vectors are parallel. 2 vectors are parallel. We know that this vector, so we know that x2 minus x1, y2 minus y1 is parallel to the vector a1, a2. What does it mean for 2 vectors to be parallel? What was it? Same slope. How do we show that? Last Friday. Same slope. Maybe check our notes. Other words, 2 vectors are orthogonal. How do we show if 2 vectors are orthogonal?
If they're equal, they're
Dot product of 0 means they're perpendicular. If they're parallel, what was it? One's a multiple of the other. So 2 vectors are parallel if one is a scalar multiple of the other. So that tells us then that whatever those points are, we have that x2 minus x1. Not today. Not everybody's taking them, so I'm holding on to them for right now. This is going to equal a scalar multiple of another vector. And so, actually what this is showing me is that if I have 2 points and I've got a vector to which we're parallel, we just a multiple there. B, D. It's some scalar multiple. some multiples. So when they are parallel, one vector is a multiple of the other. I can take away, so once, and thinking about when we wrote the equation of a line before, you had 2 points, you found the slope, and then you generalized. You took away one of the points, and you only used the remaining point. We kept one in terms of x and y. So we want to find any point along this line. If we want to find any point along this line, well, as long as we know one and we know the direction of how to get there, then we can say there's some other point on there, x, y. So, pulling that together, I can replace this x2, y2, generalize it, that for any x and a given point, for any y and a given point, we equal a scalar multiple of a parallel vector. And we have what I'm going to refer to as the vector equation of a line. Let's say we've got a point. So give me a pair of numbers. 3 and 5. And we've got vector A is
7. 2.
if we want to write the equation of the line that passes through the point 3, 5 and is parallel to 7, negative 2, it's going to be x minus 3, y minus 5 equals t 7, negative 2. Done. That's it. This is the vector equation of a line. This is the vector equation of a line. It gives us, based upon t, now t we refer to as a parameter. T is a parameter. It's any multiple. I'm going to say it's a scalar multiple we often refer to it as a parameter. And what we're doing is we're taking something, what we know with vectors, with parallel vectors and segments of that, and we're going to turn this into our parametric equations that we briefly looked at already. We call that a parameter. So whatever t is tells us how long in that one direction we're going. We can find a value of x and y. That will give us every single point on that line. Now think geometrically, a line is the set of all points that make an equation true. So what's the set of all points given a certain parameter? Now the t can change. T is an independent variable. T is our independent variable, and then x and y depend upon t. So if t is 1, just to put this out there, if t is 1, well then we've got 7, negative 2. We've got something minus 3 equals 7.
10.
We've got something minus 5 equals negative 2.
3.
So the point 10, 3 will be on that line. We can graph it out and verify that. So we've got the vector equation of a line. Now, for two vectors to be equal, the components must be equal. I'm going to take this, I'm going to modify it a little bit. Now, here's the jump that we're going to go into our parametric equations. I'm going to take this. When we have two vectors that are equal, the components are equal. So that tells me now, taking my vector equation of a line, x minus x1, y minus y1. I'm going to distribute my scalar multiple. That is t times a1. That is t times a2. Since those two are equal, I've got x minus x1 equals ta1. We've got y minus y1 equals ta2. X equals x1 plus ta1. We've got y equals y1 plus ta2. We've got a pair of equations. We have a pair of equations. One that tells us the x value, one that tells us the y value. So when we combine those two equations, this is where we have our parametric equations, or this is going to be a parametric equation of a line. And so that last example, I said our point was 3, 5, and our vector was 7, -2. That's going to turn this into, we have a parametric equation of a line where we'd have x. And I'm going to use function notation here. I'm going to turn this into function notation. X of t, meaning that x depends upon the t, is x1, 3 plus t is my independent variable times a, 7t. And I have y of t. Using function notation, y depends upon t. We've got y1, which is 5, plus a2, the vertical change. That's going to be -2 times t. And yes, I could combine that positive negative. I just wrote it hastily. So this, we've got a parametric equation for the line that passes through 3, 5 and is parallel to 7, -2. Parametric equation of a line.